So we'll have our second talk starting now. It's a great pleasure to have Fahiem Bacchus speaking. He's at the University of Toronto. He's worked extensively in many areas, including, but not exclusively, in satisfiability, constraint satisfaction problems, and optimization. And he's speaking on SAT for optimization.
So. Thanks, Sam, and thanks everybody for this opportunity. What I want to do today is I want to sort of, given the title of the workshop, the 50 years in SAT, I want to kind of give an overview of what's been happening in using SAT for optimization and talk about where we stand. So there'll be some details, but a lot of it will be kind of like an overview of where the field stands. So let's see. So if we go back, since the title of the workshop is 50 years of satisfiability, 50 years ago is when Steve Cook wrote his paper, beautiful paper, Complexity of Theorem-Proven Procedures. And in that paper, he showed that any instance of a decision problem in NP could be encoded into a similarly sized SAT formula, which is satisfiable if and only if the answer to the decision problem is true. And in fact, that SAT formula was a CNF SAT formula. And then about a year later, Richard Karp produced another nice paper which showed that there was a whole bunch of other problems, well-known combinatorial problems, that were equally as hard as satisfiability, and that all of these problems were basically equivalent, all NP-complete problems. What's interesting with respect to what I'm going to talk about today is that of these problems that Karp talked about, 12 of those 20 problems are actually decision versions of the optimization problems. Problems like clique or chromatic number, these were specified as asking the question, is there a clique of a certain size K? And that was a decision problem. But in many cases, the natural question for this is, for example, what is the chromatic number of a graph? In other words, what's the minimum number of colors needed to color a graph? Now you can convert that to a decision problem, which is, can the graph be colored in K colors? But really, often what we want to do is solve the optimization problem. So what's interesting about this connection is that it sort of gives you an immediate approach for using SAT for solving optimization. Because if you want to solve an optimization problem like the chromatic number, you can ask a series of SAT decision problems. So you can ask, can you color the graph with one color? Can you color it with two colors? All the way up to some K colors. And basically, as soon as you find the first value of K, for which the SAT decision problem says yes, then you know the chromatic number is K. And in fact, this idea persists all the way through, even to today. And all of the uses that we have for SAT in solving optimization, all of the modern techniques eventually come down to answering a series of SAT decision problems. And what has happened in the field and in this area is the types of decision problems that are asked and the encoding of these individual problems, that's where a lot of innovation has occurred in order to make more effective decision problems and smaller sequences of decision problems that can then solve the optimization problems. And a lot of this work about what decision problems to ask and how to encode these decision problems has in fact occurred in work on MaxSat. And we're going to talk about some of that work. Now, of course, neither Cook nor Karp provided useful answers to the question about how to encode a problem into SAT. In Cook's paper, he provided an encoding that was general. It was the encoding of the states of a Turing machine as it did its computation. He had to do that because he wanted to prove that every single decision problem in NP could be encoded as a SAT formula. And of course, Karp wasn't looking to encode into SAT, he was looking to encode SAT into other problems to show that these other problems were just as hard as SAT, since he knew that SAT was NP complete. Nevertheless, in the subsequent 50 years since those papers, many different SAT encodings have been developed for a range of different problems. And the importance of good encodings cannot be overestimated. In fact, modern SAT solvers don't solve SAT. They solve good encodings of SAT. Fortunately for the use of modern SAT solvers, many times when you just write down the natural encoding of a problem, and then you run, for example, SAT pre-processing techniques, you will get a pretty good encoding, and that's made SAT solvers very applicable. But if you give a SAT solver a bad encoding of even a simple problem, it won't get very far. So let me talk now a little bit more about the kind of optimization problems that we're going to look at. And we're going to focus on problems where you have a bunch of propositional variables. You have a feasibility condition, which you can think of as being a Boolean function from these from these propositional variables to true, false. And you have some sort of objective function, which maps maybe to the rationals, non-negative rational values. And in particular, if I get a truth assignment, pi, to the variables, then if I ask the feasibility function, does this truth assignment map to true, then that assignment can be called feasible. And that assignment is going to be minimal, have a minimal objective function, a value. If for any other truth assignment that's feasible, then that implies the objective function evaluated on pi is at least as small as the objective function evaluated on this other truth assignment. So that's sort of a standard formalization of optimization, but in this case, with respect to Boolean variables. Now, if you have an optimization problem of this sort, what we're going to do is we're going to use this notation, the CNF of phi at Q, to denote the SAT instance, which is the SAT decision problem, which is the instance is satisfiable if and only if there exists a feasible truth assignment whose objective value is less than equal to Q. So then the CNF conversion of this decision problem is just you convert the feasibility function to CNF, and you convert this assertion that your objective function is less than equal to Q to CNF. And if the feasibility criteria and the objective function decision are both in P, then you can get a poly-sized CNF encoding. But whether or not that CNF encoding is actually useful in practice depends on the quality and of the encoding. For some problems, can be done. You can solve these formulas with a SAT solver. In other problems, it's not so hard. Fortunately, for many interesting problems, you can solve these CNFs, and therefore you can use SAT to solve optimization. Now, like I said before, a lot of the innovation on using SAT for optimization has occurred in the area of MaxSat. So what we're going to do is we're going to concentrate on that formalism for representing optimization problems from here on. So this is sort of the general optimization function that you might think about solving with SAT. And we're going to talk about the more specific formalization in MaxSat. So in MaxSat, what you have again is you have a set of propositional variables. And now you have two sets of clauses, a set of hard clauses and a set of soft clauses. And associated with every soft clause is a weight that is positive weight, or greater than 0. And most of the MaxSat solvers are restricted to integer weights, but not all of them. So now you're going to say that a truth assignment is feasible if it satisfies the hard clauses. And the cost of a feasible solution is simply the sum of the weights of the soft clauses that it falsifies, and that a feasible solution is optimal if it has minimum cost among all of the feasible solutions. And so therefore, if you solve a MaxSat instance, you're going to look for a feasible solution. And of course, there's a strong correlation between the more general optimization function problems and MaxSat. In particular, the feasibility condition for MaxSat is simply the HARTS, which in some sense is a CNF encoding of the feasibility conditions. And now the objective function, on the other hand, is more stylized in MaxSat. What you have to do is you have to find a set of soft clauses such that when you ask what is the amount of weight that's falsified by a truth assignment pi, it has to be equal to this objective function here. And sometimes you can do this translation to a set of soft clauses, and for some objective functions you can't. But in general, if you can get an encoding of this optimization problem into CNF, you can typically get an encoding into MaxSat. Now, the practicality of the MaxSat encoding as compared to solving the individual SAT encodings might differ. In particular, these individual SAT encodings are encodings for specific values of the optimization function, whereas the MaxSat encoding is kind of an encoding that captures all values of all possible values of the objective function. So it could be that if you fix the value of the objective function to this value q, you get a simpler encoding. But sometimes the MaxSat encoding can also be quite effective. And so that's why MaxSat has become very popular and useful for solving optimization, is that often you can get a good MaxSat encoding. So a simple example, just to get us all on the same page. If you have a graph and you want to find a maximum clique, what you could do is you could say, define a propositional variable for every vertex. And these propositional variables mean that if the propositional variable is true, it means that that corresponding vertex is part of your maximum clique. And then your feasibility condition are just simply the set of clauses that, well, if you don't have an edge between Vi and Vj, then either Vi is not in the clique or Vj is not in the clique. And then now the SAT decision problem would be that, well, you have this feasibility clauses, you have these variables, and the objective function for a particular value of k would be that the sum of the propositional variables Vi is less than equal to k. And you can convert these sums to CNF. So that you can do that as a SAT decision problem. But in MaxSat, you can see that in this particular case, you get an even simpler formulation, which is that the softs just correspond of variables true as possible. In other words, I want to make the clique as big as possible. And anytime I don't include something in the clique, I pay a cost. So there's a couple other things I need before I get into sort of where we are at with respect to optimization in the current state of the art. One is that to note that any MaxSat instance can be converted to one where every single soft clause is a unit clause over positive variables. And this transformation, for example, is described in our handbook chapter on MaxSat that I wrote with Matthew Jaroslavo and Ruben Martins. So then the softs always look like this. They're always unit clauses over positive variables. So we're going to use that in what follows. The second thing that we're going to use a lot is cardinality constraints. And a lot of work has been done in this area, which is the question of how do you encode a summation over some input literals. And different techniques have been developed for doing that. So you have a CNF, which is over these input variables and over these output variables, these SK. And what you have is you want to encode the condition that if you make one of these output variables false, that's going to serve as an upper bound on how many input variables can be true. So if you make SI false, then the clauses in this encoding will force the constraint that at most k input variables can be true. And there's different encodings that have been used in MaxSat work. One of the most popular is this totalizing encoding described in this paper here. So that means that you can put an upper bound on how many input variables are true. For example, if I say that S3 is false, then I have imposed a constraint that the sum over these input variables is less than 3. And we're going to use that as well. And then the final component that we're going to use in describing MaxSat type procedures is SAT solving with assumptions. And the way this works, if you've not seen it before, is that you have a formula, a CNF formula F, and you have a set of assumptions. And these assumptions are literals that you're going to assume. And you're going to ask the SAT solver to solve F subject to those assumptions. The SAT solver will return SAT if it can find a truth assignment that satisfies the formula F and as well makes every assumption true. So it satisfies every literal in the assumptions. Otherwise, it's going to return unsat, and it will return a conflict clause over these assumptions. In other words, it'll say some subset of these assumptions, at least one of this subset must be false. You can't make all of these assumptions true. At least one of these must be false. Okay? So most SAT solvers provide this facility, and it's actually quite a simple facility to implement, but we're going to use this a lot. Okay, so that's our background. Is there any questions about that material? So if not, we'll go now into talking about how do MaxSat solvers generate a good sequence of SAT queries that allow them to efficiently solve optimization problems using SAT queries. Well, let's take the simplest approach as an example first, just to get ourselves in sync with what we're going to be doing here. So if you have a formula, a MaxSat formula, where all of the clauses have unit cost, so you have a bunch of unit cost softs, then you can do the obvious, which is the first idea that we had, which is you can ask the sequence of SAT queries, is the formula satisfiable, falsifying no more than 0 softs? Is it satisfiable, falsifying no more than 1 soft? Satisfiable, falsifying no more than k softs? So you ask this sequence of SAT queries and you stop as soon as the answer is yes. And then you know that you can find a solution satisfying only k softs. And how would you do this in practice? Well, you would have the hard clauses, and of course, you have the soft clauses, which are unit soft clauses. And what you do is you feed the negations of those soft clause variables into a CNF encoding of cardinality constraint, which sums up those soft clauses. So we know how to do that. And this CNF encoding basically sums how many soft clauses are falsified. Then all you need to do is use SAT solving with assumptions. And the first thing you do is you ask, can you solve this formula, which is this CNF formula, along with these hards? Can you solve that problem by when S1 is false? In other words, when 0 softs are falsified. And if you can't do that, can you solve it when 1 soft is falsified and when 2 softs are falsified? And you keep on going. And so this gives you a very simple way in which you can set up one formula and then through a sequence of SAT solving with assumptions, find the optimal. Now, as I mentioned before, this may not be as efficient as encoding each one of these problems individually with a fixed value of the objective function. But in the cases where it is, it can be okay. And now, of course, you don't have to go from 0 to n as we did here. You can go from n to 0, or you can do binary search. You can do different sorts of searches for finding the value where you transition from SAT to unsat. Now, the binary search idea seems attractive because you're going to do less SAT solves, but that's kind of misleading because it turns out that these individual SAT solves vary quite considerably in their complexity. So if you were to ask yourself, okay, is this solvable? And then if it is not solvable, is this one solvable? So you do some sort of binary search. These individual SAT solves might be very difficult, far more difficult than just going right across from smallest to biggest. So it's quite unpredictable that way. Now, the problem with this approach and why this simple approach doesn't really work very well is that you're not telling the SAT solver much. You're basically saying to the SAT solver when you, for example, set this assumption to be false, SAT solver will go off and look at the formula and see if you can satisfy this formula for any choice of 2 soft clauses that you can satisfy. So in general, you are giving the SAT solver the freedom to look for all possible choices and choose K, where you're going to falsify K soft clauses. And that's quite a big search space because you're not constraining it in any way. And in fact, the fundamental problem with this approach is that when you have a MaxSat formula with 1 million soft clauses, or 100,000, even 100,000, this encoding of the CNF, which sums up the soft clauses, just blows up. It gets giant. And even though you can construct it incrementally, it still blows up as the lower bound goes up. So it doesn't work very well in practice. So this layer here becomes extremely big. So this has led to sort of the state of the art for one of the approaches for MaxSat solvers, which is to use cores to guide the sequence of SAT queries you're going to make. And this idea started off with a nice paper by Fu and Malik, where what they did is they used basically the clause that you got back from the SAT solving with assumptions to give more direction to the SAT solver in the next query. And so they used what are known as cores. They call these clauses cores. And now cores are used in different ways in almost every single state-of-the-art MaxSat solver. And for our purposes, we can just think about the cores as being the subsets of negated assumptions that were returned by the SAT solver when you solved under assumptions. And these are clauses that are entailed by the current set of hard clauses. And in this context, what they're going to correspond to, we're going to see this more clearly in a bit. They're going to correspond to constraints on which and how many soft clauses must be falsified in order to make the formula satisfiable. So I'm going to give you one example of how these cores are used in kind of like a state-of-the-art way. And this is the OLL system. And this was used, for example, in some very good SAT solvers like RC2, MaxSat solvers, RC2, Maxino, University of Warsaw, MaxSat, and was first described in this paper in 2014, although the idea stems from earlier work in, I believe, answer set programming. So again, let's look at this simple example. In this example, we have 8 soft clauses, and we have a bunch of hard clauses. So the first thing we're going to do in this algorithm is we're going to try to solve the hard clauses as making all of the soft clauses true. So we're going to assume that each of these soft clauses are true. try to satisfy them all. And in my diagrams, I'm going to put a red circle around the literals that I'm assuming to be false. So I'm assuming that the negations of these soft clauses are false. In other words, that the soft clauses are true. So that's your first sat solve. Now suppose you get unsat. I can't do it. I can't satisfy all 8 soft clauses. And I get back then some subset of these assumption literals negated, which is implied by the formula. And let's say that we get, well, I can't satisfy all of the soft clauses because I must falsify at least one of B1 to B5. So now what I'm going to do is I'm going to build a new cardinality constraint whose inputs are exactly the literals from this core, this clause that I got back from sat solving under assumptions. And so I build myself a new cardinality constraint, which sums up these literals that I got back and adds these new summation literals. And now what do I know? Well, I know that the previous sat solve has told me that one of these soft clause, one of these literals must be false. Therefore, this summation must add to at least 1. So I can set S1 to 1. And I want to falsify no more than that. I know that I have to falsify one soft clause, and it must be one of these soft clauses, but otherwise, I don't want to falsify any more. So then I can assume that, well, let me make sure that among these clauses, I falsify at most 1. So I assert not S2. And the remaining soft clauses, I must make them true. So I assume all of those. Now I do a sat solve again. But I wanted to notice the first thing is that I've built myself a cardinality constraint, but that cardinality constraint is over only the literals that appeared in the core, which is a much, much smaller subset than the set of all soft clauses. So typically in most instances, you might get 50 soft clauses in your core, even when you have 100,000 soft clauses. So you're building yourself a cardinality constraint over a very much smaller set of soft clauses, and therefore the size of this cardinality constraint in terms of the CNF representation is much smaller. So, okay, and the second thing you've done is that you've not only told the sat solver, go and try and find a satisfying solution which falsifies only one soft clause, you've told it that of the ones that you must falsify, you can only falsify one of these. So you've restricted the choices that sat solver can look at in terms of which next one it should falsify. So again, you've made the sat solve much simpler. So what you do, okay, is you do this additional sat solve. And suppose you get unsat one more time, and you get a new core. Well, again, the new core has to be a negation of one of these literals here. That's what the sat solving under assumption does for you. And so, for example, say that you get that, well, you know, I have to make at least S2 or not B6. One of those has to be true. That's what the sat solve is telling you. So now you build, again, a new cardinality constraint over those 2 input variables. And you've created 2 cardinality constraints that you've added to the formula, which had these original set of feasibility constraints. And now, again, you know that for this cardinality constraint, at least one of its inputs must be true. For this cardinality constraint, at least one of its inputs must be true. But you don't want more than two of them to be true, so you set this. You don't want either one of these to be falsified, so you set this. And you don't want more than one of these from this cardinality constraint to be true. And now you can set yourself up the next SAT solve, which involves these assumptions. And if we look at this more carefully, it's not hard to see that what you've done here is you've basically gotten information from the two SAT solve you've done that one of these literals must be false. So you've allowed the SAT solver to do that. And that either it's the case that two of these, that's what this S2 means, two of these literals are falsified, or this one is falsified. And that's what this cardinality constraint encodes. And that's the information you're given to the SAT solver when you're asking it to find now a solution that falsifies at most two solve clauses. You've also given it this information you've gotten from the other previous two SAT solves. And that makes it much more efficient. And you keep on going. And this works pretty good. It's one of the best ways of solving SMAC-SAT. Now, some interesting questions that has arisen from this line of work is that there are many different ways of generating these new cardinality constraints from the cores that have been developed. And some ways are more efficient than others. And it's not yet clear. There's a deeper understanding of where the efficiency differences lie remains an open question. For example, can you argue, for example, that this particular OLL method is using all of the information that it got from the previous SAT solves? It seems like it is, but it would be nice to formalize that notion. Now, the other issue with this approach to doing optimization is the SAT decision problems are growing in size after every core is found, because you have to add a cardinality constraint to the SAT formula every time you do one of these iterations. And so for problems where you need many iterations, what will happen, does tend to happen, is the SAT decision problems become too large or too hard to solve. And this is particularly a problem when you start dealing with non-unit weighted solve clauses. Because there, what happens is that, especially with instances with many diverse weights, what you end up with is you end up with many iterations. Because basically what's happening is you have to start examining all of the possible different sums that these diverse weights could generate. And as you might know, it basically, it doesn't take too many diverse weights to generate a tremendous number of diverse weights in their subset sums. So these schemes, for example, on problems with more than 50 distinct soft clause weights tend to not work very well. Now, an alternate approach is an approach that's come out of my research and my students' research, and also picked up by others, is an implicit hidden set approach, which tries to use a sequence of SAT solves that are quite different from the core-based approaches. And this work originated in the PhD thesis of Davies in 2013. And the idea is very simple. So you are going to call a clause entailed by the formula F. We're going to say that that clause is a core if it contains only negated soft clause variables. So for example, if the soft clauses are B1 to Bn, then a clause like not B2, not B5, not B10, not B12 is a core. because it only contains negated soft clauses. In other words, it's saying, this clause is saying that at least one of these soft clauses must be falsified. So that means that if you have a set of cores, a whole bunch of such clauses, and you have any truth assignment which is feasible, any feasible truth assignment, then that feasible truth assignment must falsify at least one soft clause from every core in this set K. In other words, it must satisfy every clause in K. Now, if we look at the set of soft clauses that are falsified by a feasible truth assignment, pi, let's call that set A, we see then that if we regard these clauses as being sets of of literals, we see that this set of clauses that are falsified by pi is in fact a hidden set of my set of cores. In other words, it has a non-empty intersection with every member of my set of cores. So that tells us then that if we could compute a minimal cost hidden set of my set of cores, that means that since every feasible solution falsifies a set of clauses that is a hidden set, the cost of every feasible solution is going to be an upper bound. In other words, the minimal cost hidden set is going to be a lower bound on the cost of any feasible solution. So that means it's going to be a lower bound on the cost of an optimal solution. So therefore, if I can find any set of cores and any feasible solution where the cost of my feasible solution, in other words, the sum of the weights of the clauses it falsifies, if that cost of that feasible solution is equal to the weight of the minimal cost hidden set, then I have a verification that my feasible solution is in fact an optimal solution. And this leads to this very simple algorithm for finding an optimal solution. Now, this is an algorithm that is no longer used in practice. The version that's used in practice, like for example, in my MaxSat solver MaxHS, uses instead upper and lower bounds. So it looks much more like a traditional optimization algorithm. But this is the simple algorithm that gives us an idea of how this works. You start off with an empty set of cores and a hidden set of that empty set of cores, which of course is an empty set too. You then do a SAT solve under assumptions. You solve the hards and you ask it to also solve all of the softs except those that are in the hidden set. And if the result is SAT, then you found a SAT of optimal solution. If the result is unsat, then you have returned yourself a conflict. And that conflict you can add to your set of cores, and now you can recompute your minimal cost hidden set. And you go again. And why does this work? Well, if this is satisfiable, what can pi falsify? It can only falsify the soft clauses that are, it has to satisfy all of the soft clauses that are left after you remove the hidden set. So therefore, the cost of the soft clauses it falsifies is upper bounded by the cost of this hidden set, which is, of course, a minimum cost hidden set. And of course, we know that the bound goes the other way. So it must be that the cost of pi is in fact equal to the cost of the minimal cost hidden set, and it must be optimal. And on the other hand, if you get unsat, you have returned yourself a core. So you have to terminate because there's only a finite number of cores. Now, you need, of course, a method for computing minimal cost hidden sets. And in practice, integer programming solvers are often used for this purpose. Like I said, the modern approach to using this utilizes upper and lower bounds rather than this more simple algorithm I just presented. Now, in some cases, it turns out that the hidden set problems that you produce, you can show that they can be solved in polynomial time. And that was, for example, used in this nice paper to show that under a particular encoding, they're called the dual-rail encoding, this approach, implicit hidden set approach, can solve pigeonhole in polynomial time because of the hidden set problem that's generated can be solved in polynomial time. And you only need to do this, generate a polynomial number of cores, all of which can be done in polynomial time. So that paper sort of gives you an indication that this method gives some interest in different power over simple set solving. Now, one of the difficulties, and this is what I sort of last thing I want to talk about, of this implicit hidden set approach is that, well, it does fare better when you have a large number of diverse weights, because then actually the hidden set problem becomes easier to solve because there are less symmetries in the hidden set problem because the weights are so different. But the approach can require computing an exponential number of cores. And this is some recent work that I've done, and let me explain this idea. Let's define this notion of what I would call exchangeable set of soft clauses. And for simplicity, let's just restrict ourselves to unit weight soft clauses. You can lift this notion of exchangeability to weighted soft clauses too, but it's simpler to think about when you have unit soft clauses. So say that we have a subset of soft clauses. So we have the formula, it has some soft clauses, and we have a subset of soft clauses, and the size of this subset is n. We're going to say that this set of soft clauses is exchangeable when for every feasible truth assignment that happens to falsify k soft clauses in our set E, there exists another n choose k feasible truth assignments, all of which satisfy exactly the same softs outside of E and falsify a different size k subset of E. In other words, it doesn't matter which particular soft clauses in E you falsify. All that matters is that you falsified k soft clauses, and you can falsify any k soft clause and still get a feasible solution. So that's this notion of exchangeability. And it's a semantic notion of symmetry. And as we discussed in Morin's paper, it turns out that if you look at most MaxSat formulas, even formulas that are specifically designed to have this kind of exchangeability, they are syntactically never symmetric. So if you run standard symmetry detection mechanisms, which work on the syntax, they never detect symmetries. But these semantic symmetries do seem to exist quite frequently. Now, what happens when you have an exchangeable set of soft clauses? Well, it leads to an explosion in the number of cores that the formula has. And it's not hard to prove that if you have a core, C1 to Cm, in other words, a set of soft clauses, one of which has to be falsified, and you have an exchangeable set, E, then if the intersection, if k elements of this exchangeable set appear in our core, in other words, the size of the intersection between the core and the exchangeable set is k, then it turns out that there exists n choose k other cores that are similar to this core. In other words, what you can do is simply replace the set of soft clauses that are in E, and you can get another core. And so you get this explosion in the number of cores. And in Davies' thesis, what she proved is that if you have the entire set of soft clauses being exchangeable, you have a formula where the entire set of soft clauses are exchangeable, then she proved that the implicit hidden set approach will require an exponential number of cores to make the lower bound reach the optimal cost. I don't know if, or my conjecture is that this holds also when you have only a subset of soft clauses that are exchangeable, but I haven't yet been able to prove that. Then with this idea, what we did in 2020 is we developed a method that tried to circumvent this problem of the exponential number of cores that might be required because of exchangeable soft clause sets. In particular, what we did is we exploited the fact that you will get a lot of soft clause with clauses from this exchangeable set. And we used that idea to detect when sets of soft clauses were likely to be exchangeable. And then when we detected a set of soft clauses that are likely to be exchangeable, we developed a method where we could abstract those soft clauses and talk about their summations rather than their identities. How many clauses in this set are falsified rather than which ones, and allowed the SAT solver to generate abstract cores, which could compactly represent basically an exponential number of ordinary cores. And this method worked very well in practice. It allowed MaxHS, for example, to be the best performing SAT solver in the unweighted category in last year's competition. But the theoretical underpinnings of this is still work in progress. And I think the other thing that's quite interesting about this idea is that these kinds of symmetries which foil the solver seem quite common. And it's interesting that in the previous talk that this also seems to happen in ordinary SAT solving, where these PR clauses seem to get around some of that. So that's kind of my overview of where we're standing with using SAT for optimization. And I welcome any questions.
All right, thank you for the talk. Very nice. I'll applaud on everyone's behalf. And let's see, please either speak up and ask questions, looks like it, or put something in the chat window. So please, anyone can volunteer. While you're formulating your questions, I have one question myself. Earlier in the talk, you talked about the summation, the CNF encodings of the cardinality constraints blowing up very, very badly. What does that mean? Does that mean quadratically or exponentially?
Yes, it's quadratically. And so when you have 100,000 inputs, you're out of luck.
Okay. Right. Okay. I mean, you could do certainly quasi-linear in principle, but I assume people have tried that. And
yes. So what happens is that you get this trade-off. There are encodings which are, I don't know the full details. There are certainly polynomial encodings, but I think it's quadratic. You get this trade-off where you can encode it just simply, for example, as adders, but then you don't get much propagation. You don't get much inference from going backwards, which is what you need, unit propagation. So they become quite weak until you've set lots of the inputs.
Mm-hmm. Okay. All right.
But even I think even with the, like if you encode it as adders, the other problem, of course, is the adders have XORs, and you start to get a lot of XORs in your formula, and that also slows the solver down. So it's sort of like, it's more of a practical than a theoretical question, really, which is there kind of like no nice way of encoding these very large cardinality constraints.
Okay. Armin has a question in the chat window.
Right. So you're still using ILP solvers. Yes, I am. Now, I suspect that for the case where you have unweighted soft closes, you could use a SAT-based approach, maybe by recursively call in a MaxSat solver, and that might actually work just as well as the ILP solver. What happens, however, is in the unweighted case, it doesn't work as well. The ILP solver seems to work much better in the unweighted case. In the weighted case, we have many diverse weights. So I would like to move away from using the ILP solver because what we're using is currently proprietary software, although it's available to academics. But I haven't found an alternate approach. The other thing I would say about the ILP solvers is that they give you other resources which are useful. So we had another paper where we did reduced cost fixing, which is a ILP technique, and that also is very helpful in solving these MaxSat formulas.
There's a question from Chiaran Makrish. He writes, are you convinced the commercial MIT solvers are even producing the right answers in the weighted case?
No, we're not convinced. And in fact, verification of the answers is difficult. What we do know is that the way the solver will work is that the MIP solver will produce a candidate hidden set. The SAT solver will then produce a feasible solution with that cost. And that's when we terminate. Now, if the ILP solver is incorrect, its bound will be wrong, but we still will get a feasible solution. So if the SAT solver is correct, of course, it may also be incorrect. You know that at least the solutions you're getting are feasible and they have that cost. Where you don't get the verification is that you don't get the verification that that's the optimal cost. And to get that verification, what you would need to do is you need to prove that the next lowest cost is unsat. So you could potentially do that if the problem is not too difficult. You could find the optimal solution and then in a separate SAT solving episode, verify that you cannot solve the problem with anything less than that, and then check that proof. So then you can easily verify that your feasible solution is a feasible solution that achieves that cost, and then you can check that the any other thing is unsatisfiable with the proof. So you're not really tied to the exactness or the correctness of the commercial MIP solvers.
Okay. Any other questions? Comments? Feedback?
So one thing I would say as well, which is an interest, and maybe there's some other responses I can get, is that these cardinality constraints, I think, are very interesting. What's happening when you solve these MaxSat formulas is you're kind of generating extension variables. It's not hard to see that, for example, S2 is really an extension variable. It's saying that at least one of these inputs is true. And the relationship between adding these kinds of cardinality constraints and adding extension variables is an interesting one that I wonder whether or not a judicious use of detecting when this might be useful in ordinary SAT solvers could also be beneficial.
There's another question from Armin. I'll read it out here. In
Okay.
Adnan's talk a couple days ago, he used as costs the product of literal costs. Does this fit your unit soft clause model?
No, but you can, of course, if, for example, you use a MaxSat solver like MaxHS, which allows you to use um, floating point weights, you can, of course, use the logarithms. So the sum of the logarithms would then be the products. So that would be a simple translation. So the product of the literal costs are used to get yourself probabilities. So that's where that comes from. So if you do the log transformation, you can get a MaxSat formula where you're adding up the costs. And in fact, MaxSat has been used in this way to solve most probable explanation problems, MPE problems, where you are using the logarithm to get convert the product into the sum.
Very good. Last chance for questions or comments. Otherwise, thank you again, Fahiem, and also Marine, for two really excellent talks. Very, very nice to have you here today. So, and there's a comment in the chat window that for those of you who are Simon's participants, there's a possibility to go to GatherTown afterwards and chat there on the link in the chat window. So again, thank you everyone, and see you next week, or in GatherTown actually.